Let's welcome Mark Stewart.
One of the things I would start out with, I guess, is to try and at least convince you a little bit of the relevancy of this topic. And this comes from the back of one of my notebooks. I use a little notebook system. And it says, this notebook was made of sustainable materials. That's a word that gets thrown around a lot. It's a word that gets thrown around a lot in business nowadays because many businesses are going to what are called sustainable practices. Well, what does that mean? Well, here's some definitions. The first one is pretty useless. Capable of being sustained, of relating to or being a method of harvesting or using a resource. Number one is that this one, of or relating to or being a method of harvesting or using a resource so the resource is not depleted or permanently damaged. And that's what we're going to talk about today. Because in effect, what is happening is that the climate is changing, and those changes are going to affect the way that we do almost everything in our lives. And climate change is kind of interesting because there's a lot of science which just goes by and nobody cares about it. All of us are carrying around these quantum electromechanical devices, right? We just use them. I don't see any big public arguments over quantum mechanics. If people knew about quantum mechanics, they might want to argue about it. But there are public arguments over evolution. Why? Because evolution conflicts with a literal interpretation of Scripture. And so for people who have a profound faith, that particular brand of science conflicts with their beliefs. And so it becomes an issue in many states, such as Texas. There are boards of education to try and introduce textbooks that give a so-called balanced view between evolution and creationism. So evolution is something. Well, climate change turns out to be another contentious issue. Why? In the last 200 years, we have created a really astounding technological civilization. China alone, in the last 20 years, has brought more people out of poverty than in all of human history. How have we done that? We've done that with cheap and abundant fossil fuel energy. And that's why we are all here. It's why you guys study business. That's why you're going to make a living. Right? So this is what's created our society. Well, as you'll see today, is I'm going to talk about two questions. The first question is the climate changing? That's the first question to ask, right? Climate change, okay, is it changing? How do we know that? And the second question to ask is, okay, if it's changing, how do we know it's us? And so we have this paradox of perhaps we are using something, the climate, in an unsustainable manner. But the cause of that unsustainability is the very thing that has brought us to this point in our technological society. Which means that my discussion today is about science, but there are far, far deeper and important political, social, economic, and philosophical questions associated with this whole thing. My son is an industrial engineer. He works for what's called a multimodal transportation company. And so he's really interested in what's called supply chain. The idea that we no longer have huge warehouses of stuff next to a factory. What happens is that you have just-in-time delivery, and so you rely on the supply chain. Well, he did a study of supply chain disruptions and found that almost half of all supply chain disruptions come from extreme climate events. And so it's really important nowadays to all manufacturing to understand, is the climate changing? How is it changing? How is it going to influence my business? Right? So I would say to you that this is not an arcane and controversial science topic. It's something that affects everyone's lives. And John and I thank you because we had a wonderful ride using lots of cheap and abundant energy. And now you guys are going to have to do something about the problems. But thanks, guys. It was great. All right. So, two questions. A media interest group at Harvard asked a lot of people some questions, and one of the questions they asked people is, if you could ask a climate change scientist one question, which question would you ask? And people that were at both ends of the scale, completely unconcerned about climate change or denying it, and people who were deeply concerned about it, came up with the same two questions. And these are the two top questions. How do we know that climate's changing, which is a very reasonable question. And the second is, how do we know that human activity is the cause of climate change? So that's what we're going to go through. All right, an introduction. All right, what is that right there? It's a space shuttle. It's the International Space Station. There are people up there now. There was just a spacewalk a few weeks ago that everybody's worried about. All right, what's that right there? That's the vertical stabilizer on the now no longer operating space shuttle. Right? All right, what country is that? Looks like a boot.
Italy.
Italy, yeah, right. So this is flying over the Mediterranean and Aegean Sea. What is that thin blue line on the horizon? That is the atmosphere. That little thin blue line. It's this little eggshell clinging to this rocky ball hurtling through space. All right, we need to make a distinction between climate and weather. We all get it wrong. And when my relatives ask me, okay, so what's the weather like in Tampa? You know, a lot of my relatives live up in central New York. And so they go, well, what's the weather like in Tampa? You go, well, you know, in the winter it can be really nice. Sometimes it gets cold, but most of the time the temperature's really good. Rain sometimes. But summers are, you know, rainy and can get really hot. I have not told them the weather. I've told them the weather I expect to happen. That's climate. Climate is the long-term average of weather, typically 20 or 30 years. And the weather in the past few weeks has been a good example of that, is that a lot of the media now people go, hey, what's with this global warming? It's really cold out. You know, well, yeah, it gets cold in winter. And I have a slide in here that will talk about that. But we all tend to think, when you're asked to describe something, you think of your most recent episodes or occurrences, and you kind of average that together really quickly, and that's what you come out with. And so we tend to categorize things by what most recently happened to us. And we also tend to categorize things by where we are. Go, hey, what's with this global warming? It's really cold. Yeah, it really is. It's cold in about 1/3 of the northern hemisphere right now. But for the same reasons we're cold, 2/3 of the northern hemisphere is right now experiencing above average temperatures. We are not the world. Okay? We are here in Tampa. As Mark Twain said, climate is what we expect, and weather is what we get. All right, so is the climate changing? I don't think anybody argues that we don't have any thermometers. We've been reading thermometers since the 1700s, and we've been reading them consistently in lots of places around the world since about the mid-1800s. That's in the British Empire. For North America, we go back to about 1880. And so we have a series of thermometer readings from around the world, and what different groups do is take those records and they average them. And there are different ways of averaging to come out with a global average. So you end up with these slightly different global average temperatures. And by the way, see that word anomaly? In normal usage, what we mean by that is we mean something strange or out of the ordinary. All we mean in this case is a temperature anomaly as I take a long-term temperature average, say at the Tampa weather station, 1951 to 1980, and I average the temperatures. And then I take the temperature of any given year and I subtract it. And so what that tells me is that it tells me the relative change in temperature at that station. So it means I can compare Key West to Minneapolis, because I'm not comparing absolutes. But that's all that anomaly means. It's just a difference from a long-term average. And you can see this goes back to 1890 on this graph. GISS is the Goddard Institute for Space Science. That's NASA. HAGCRU is the Hadley Meteorological Center in Great Britain, and the Climate Research Unit at one of the universities, East Anglia. This is NOAA, National Oceanographic and Atmospheric Agency. This is Remote Sensing Systems, which is a private outfit which interprets satellite data. And this is the University of Alabama, Huntsville. These last two are satellite estimates of the temperature of the lower atmosphere. And they obviously only start out here in 1979. So there's the red and the beige one here. What you can see is that in the early part of the 20th century, there was a rise in average global temperature. And then from about the mid to late 1930s through about the 1960s, the temperature basically stayed about the same. And then starting in the late 1960s, around 1970, there was a rapid increase in average global temperature. And these data sets, which use different averaging methods and these satellite methods, which are completely different because they're not thermometers, all agree quite well on the temperature. Now, about 2.5, 3 years ago, there was another group that gave us an additional estimate. And this is called the BEST group, B-E-S-T. The acronym was deliberately chosen. It was led by a particle physicist named Muller. And he had been really popular to go before the U.S. House of Representatives committees on the environment because he denied that global warming had occurred because he cast doubt on the data. He thought the data were bad. And so he announced that he was going to head up a group which was going to do it right. Particle physicists have a lot of hubris about their ability to handle big numbers. And they're probably right, because they literally extract data from millions, if not billions, of data points. So they do know how to handle large numbers. So they used a statistical method which used about 30,000 different climate records around the globe. These other ones use about 4,000 or 5,000, but these guys could take little pieces of record and statistically put them together. And this is what they came out with. All those colors in there, it's NASA, NOAA, Hadley, and the black line, which you can't distinguish, is the Berkeley group, the Berkeley Earth Surface Temperature Group, BEST. What's interesting about this group is that about 1/4 of their funding came from the Koch Foundation. Charles and David Koch. If you know who the Koch brothers are, most of their very substantial fortune comes from the oil and gas industry. They are famous for funding science. If some of you have seen some of the science, like NOVA programs on PBS, you'll see that some of it's funded by the Koch Foundation. So they do fund science, but they don't like climate change. And so they funded partially this group because Muller was a denier and got cast into doubt, and everybody thought that he was going to come out and say that, wow, there's all this data wrong. Well, he came out and said he's converted, and he's a climate believer. And they then did another study, which basically they came out with a conclusion that it's the increase in carbon dioxide. So he doesn't appear before many U.S. House of Representatives committees anymore. This is a different measure of changing temperature of the Earth. 70% of the Earth's surface is water. And there currently is an imbalance between the amount of energy coming in from the sun and the amount of energy sent back into space from the Earth. And there's slightly more energy coming in than is going out. Not much. It's about a 60 or 70 watt bulb sitting in a square meter. Okay, so not a lot, but if you think about doing that over the entire Earth, it ends up being a lot of energy. And the result is that that heat is going largely into the oceans. And so this axis here is heat content, not temperature, because it takes a lot of heat to change the temperature of water. If I had a cubic yard of dry air sitting here, and in a box over here I had a cubic yard of seawater, it takes about 4,000 times more heat to change the temperature of that water at 1 degree Celsius than it does to change that dry air at 1 degree Celsius. So most of the heat from this imbalance is going into the oceans. This is the from the surface to about 7,000 feet below sea level. In the oceans, this is the heat content. And what you can see is that the heat content has been rising. Remember that piece on the atmospheric temperature that went from the 70s and went up? And that heat content is also rising. These data out here, the red stuff, since about 2002, we've had some really, really good data. We have these, they're called Argo floats. Basically, it's this device. It's about maybe 10 inches in diameter, about 6 or 7 feet tall. And it's a buoy, and it drops down to 2,000 meters, about 7,000 feet below the surface. And then it comes back up to the surface and measures temperature and salinity, broadcasts the data out to a satellite, and then goes back down. And at any point in time, each float lasts a few years, and at any point in time, about 3,500 of them all around the world ocean. So it's really, really good data. So this is good data that we have out here. All right. There are other indications that the climate is changing. This is in 2010. This is Manaus, Brazil. The Amazon is back there. In 2005, the Amazon basin experienced the most severe drought on record. And then in 2010, it experienced an even more severe drought. So one of the things that is occurring is an increased frequency of drought during the 20th century. Warm air holds more moisture than dry air, than cool air, excuse me. So as the temperature warms, more moisture can come from the soil into the air. And so the result is that as the climate has warmed slightly, we have had a tendency to create more moisture in the atmosphere, and that a lot of that moisture is coming from soil. So we're seeing an increased frequency of drought. Now, that warm air holds more water. But whether or not it rains depends not on the total amount of water in the air, but the relative humidity, the relative amount of water that the atmosphere can hold at that temperature. And so if it's warmer, there's more air there. So when we hit 100% humidity and we can condense water and it rains, there's more water. So what is happening is that in some areas of the globe we're seeing more rainfall. For example, mid and high latitudes. But interestingly, most of the increase in rainfall is coming in extreme rainfall events. So this is the Midwestern United States from 1960 to 2010. And the principal increase is in the events 3 or more inches per day. They've increased by about 53% over the previous occurrence. And in New England, this again is extreme rainfall events, number of events per year, and those have also increased as we go out from 2000 to 2010. So the probability of more extreme rainfall events is increasing because warm air can hold more water. Now, one of the other things that happens is there's more solar energy strikes the Earth, is absorbed by the Earth in equatorial regions because sunlight is almost straight down, the sun's directly overhead. And so that warm air rises, it cools, and as it cools, it then descends. And where it descends is about 25 degrees north and south latitude. Right? Well, what is around the globe at 25 degrees north and south latitude? Like the Sahara, the Middle East, these are the desert regions of the globe. What is happening is that as the tropics are getting warmer, that circulation is being enhanced, and these cells are getting bigger. So the northern boundaries of these circulation cells are moving towards the poles. So what that means is that this dry region here is moving into southern Europe. This is the difference in winter rainfall in Europe from 1900 to 2010. And basically red means less. And the important thing in the Mediterranean is winter rainfall because it's a Mediterranean climate, which means it rains in the winter and it's really dry in the summer. And so if you have a decrease in winter rainfall, it means a really big decrease. This one's kind of important. What country is that right there?
Syria.
Syria. What happened in Syria about 2.5, 3 years ago?
Revolution?
Civil war started. One of the things that happened in Syria is, especially in western Syria, there was a severe drought. Many farmers were forced off their lands. They moved into the cities, and there was price of food went up. There was a lot of civil unrest. And so some people are saying that some of the start of the civil unrest in Syria was because of this severe drought that had been experienced starting a few years ago. This is a probability distribution that you guys are all very familiar with. This is the infamous curve. Do you grade on a curve? You know, the bell curve. Basically, it expresses, this is the mean or average value, and then this curve tells us the probability of extreme events. And in this case, this is temperature, and this is the average June, July, August temperature in Moscow. And so the average June, July temperature in Moscow, this is the average temperatures. It's not 0 degrees Fahrenheit, it's warmer than that, but it's still pretty cool. But basically, this is degrees Fahrenheit above or below the average. And these all are events that define a normal distribution. These are 3 intense heat waves that occurred. This is 1999, 1972, and then the one in 2010. 2010 is the warmest year in the thermometer temperature record going back to 1880. And that was a very, very severe heat wave in western Russia. About at least 3, probably 4 standard deviations, which means it has a probability of about 0.01% of occurrence in any one year. It's called a 1,000-year event. And it created probably 30 or 35,000 people died as a result of that heat wave. Heat waves are becoming more common. You may remember the 2003 heat wave in France that also killed about 30 or 35,000 people. This is one I just added because it's just starting to get in the news recently. As you know, the past couple of weeks, it's gotten really, really cold up in the Midwest and New England. And so people are saying, hey, it's cold. Where's this global warming stuff? Well, these are Minneapolis, St. Paul, Atlanta, and Tampa. This is 1970 at this end. This goes out through 2012. And this is the number in Atlanta, the number of nights below 32 degrees Fahrenheit. Minneapolis, it's cold in Minneapolis. Number of nights below -10 degrees Fahrenheit. And for Tampa, it's below 45. And there's the actual data, nights per year. And there is a linear regression fitted to it. Yeah, it got cold last week, but on average in the last 40 years or so, we are seeing fewer frigid nights and cold outbreaks than we saw in the past. We have not had a cold outbreak like the one we had last week since 1999. Prior to that, during the 20th century, the average was an outbreak like that once every 4 years. And so what's happening is we're actually getting fewer frigid nights. But it still gets cold in the wintertime. And if the Arctic actually is warmer this year than it is normally, but it still gets really cold in the Arctic. And when that Arctic air manages to get down because of a big dip in the jet stream, we get really cold. So the idea that it's cold in the winter does not negate the idea that the climate is changing. What you need to look at is you need to look at long-term averages. All right? If I have a distribution which has noise around some average value, then if I randomly select from that distribution, there should be an equal probability of getting values above or below the average. Right? If the mean of that distribution is shifting, then that no longer will be true. All right, from 1950 to 1969, this is in the lower 48 in the United States, there were 52% of record lows and 48% record highs. This is the relative balance between record highs and record lows. Every winter we set new record lows. Every summer we set new record highs. If the distribution isn't changing, they ought to be about the same. And so for this period, 1950 to 1969, they didn't change. 1970 and 1989, pretty much the same. 1990 to 2008, 37% cold, 63% warm records. 2009 was almost 50-50, 45. 2010, 2011, and these data were done in 2012. So this is the first 6 months of 2012, and it was a record. It was the warmest March on record in the United States. And so this spring and winter was actually very, very warm. This is just the month of July in 2012, had a big heat wave. But basically what's happening is we see a shift, and there are fewer record lows each winter and more record highs each summer. This is the percent of lower 48 land area experiencing extreme temperatures. Blue means cold, red means warm. Here is the Dust Bowl, which was another very warm period in the United States. And in that case, about 30% of the United States was affected by extreme high temperatures. But by the time we get out here to the last few years, in 2010 is when these data go to, we have 60% of the U.S. affected by extreme temperatures. So has it been, have we seen record temperatures in the past? Yeah, we sure have. But what we're seeing is more and more and more area of the lower 48 being affected by extreme temperatures. And most of those extreme temperatures are warm, and fewer of them are cold. But we still get cold outbreaks. It gets cold in the winter. One of the other things that we can notice is that if you put an ice cube on the table, it melts. So if the general global climate is warming, then we would expect that ice will tend to melt. And that is what we're seeing. This is the Arctic sea ice volume. The Arctic Ocean freezes every winter, and part of that ice melts every summer. And we can calculate the volume from satellite measurements. The satellite data go back to the 1970s. And so what you can see, these data go out to 2010. And so this is March, which is the maximum ice extent in the Arctic. And this is September, which is the minimum ice extent. And in both of them, the amount of ice is decreasing. And it started to decrease really rapidly in the 1990s. If you just fit a second order polynomial, this is suggesting that within this decade, we might have an ice-free Arctic Ocean in the summertime in September. This is the Greenland ice sheet. I'll show you another slide in just a second. Prior to around 2002, it was difficult to measure what was going on with major ice sheets because they had to figure out how much snow came in and how much ice melted. And so we had these estimates here. This is called the mass balance. It's the difference between snow coming in and ice melting. But then starting in the 1990s, our measurements started to show, this is altimetry. It's by looking at the elevation of the ice. And then this is a satellite called GRACE, Gravity, Recovery, and Climate Experiment. I'll show you a slide in just a second for these. But basically, all of those are showing a strong decline in the amount of ice in the Greenland ice cap. This is Greenland GRACE data here. This is year. Now, there's a problem with these data. 2002, 2012. Remember I told you we need at least 20 years of data? These are too short. Not enough time. Looks like a really robust progression, but we're not going to be able to tell. It's going to take us about another 5 years to reach statistical significance for Greenland, and for Antarctica, it's going to take us another 7 to 8 years before we reach statistical significance. But you can see the trend. Now, the GRACE satellites are pretty cool. They're two satellites that are several hundred kilometers apart, and they have a microwave radar system that tells the satellites how far apart they are. And the gravity, we all think of gravity in a scale as being constant, but actually the force of gravity changes a little bit over the surface of the Earth. So if you go over an oceanic trench, gravity's less. And so these satellites go down, and they get closer together, like that. If you go over a mountain range, gravity's higher, so the satellites get farther apart. And so by telling the distance between the satellites, they can measure the change in gravity. If you go over the same place on the Earth every 2 weeks, any change in gravity is a change in mass, like less water or less ice. And so we can directly weigh the Greenland and Antarctic ice sheets through these satellite measurements. And in both cases, both of them are losing mass. They have a negative mass balance. There's less snow coming in than ice being melted away. Now, when you warm something up, it expands. I showed you that there's heat going into the oceans. So the oceans are expanding, and the result is sea levels going up. There's also a contribution from melting ice. At the moment, that's not the most important contribution. It may become more important in the coming decades, but at the moment, it's just this thermal expansion. And so we have good records from tidal records, and now we also have satellites. And you can see the satellite record has this little wobble in it. That's because in the summertime, the ocean's warmer, so sea level goes up, and in the wintertime, the ocean's colder, and sea level goes down. So basically, you can see that sea level is rising, and right now it's rising at a rate of about 3 or 4 millimeters per year. It doesn't sound like much, it's about like that. Right? But if you carry that out to 2050, it's about a foot of sea level rise, but it's accelerating. So we would expect sea level to rise about 1 to 2 feet by mid-century. The important thing is when you know the probability of a storm surge, that change of 1.5 to 2 feet means that a 100-year event, something that has a 1 chance in 100 of occurring in any 1 year in the New York City area, like Sandy, will have a 1 in 10-year event, a probability, a 1 chance in 10 or 10% probability. So changing sea level a little bit changes the probability of a given storm surge. So sea level's rising. This is really important to us in Florida. The other thing that happens is a barrier island like Sand Key over Clearwater. That's just a pile of sand. It's in equilibrium with sea level. If sea level goes up, that barrier island moves landward. And in Florida, they move landward about 500 to 1,000 feet for every foot of sea level rise. Think about standing in front of those condos in Sand Key and turn around and say, where's 500 feet? Okay? It's on the other side of those condos. And so we're going to have a lot of trouble maintaining our coastal tourist economy in Florida because we're going to have what we call beach erosion. It's not really eroding, the beach just wants to be back there. And so that's going to be a big problem for the Florida economy. We're going to have to figure out what to do because up until now, a large part of beach renourishment, pumping sand under the beaches, has been covered by the federal government. But as you all know, the federal government, or representatives of the federal government, are less happy about spending money. And I don't know for how long people in Lincoln, Nebraska are going to want to pay for pumping sand on the St. Pete Beach. And so that means we're going to have to pay more. It also means insurance costs will go up. And so all of this ends up affecting our local economy. One of the other things that's happening is in the western United States, it's getting warmer. It's 1 to 2 degrees Fahrenheit warming in the western states. And because of that, it's gotten drier. And the result is trees are stressed. And so you can see this riot of fall color. No, wait, those are pine trees. Pine trees don't have a riot of fall color. Those are dead pine trees. Tens of millions of acres of conifer trees in the western United States and western Canada have died. And the reason they've died is they've been attacked by this little beetle called a bark beetle. And what happens is bark beetles and conifer trees have been together for 60 million years, and so they should be in balance. What's happening is that the warmer temperatures are allowing more bark beetle larvae to winter over and not die, so there are more bark beetles. The next thing that happens is when a bark beetle bores into a tree, the tree defends itself by exuding sap and kind of surrounding the bark beetle or the larva. Well, when the trees are water stressed, they can't do that. And so what's happening is that we're losing huge amounts of trees. In the last few years, 50% of the marketable timber in British Columbia has basically died. A friend of mine spends a large part of his summers in Montana each year at Flathead Lake. And he said the people out there are just kind of scratching their heads because things are starting to look really different. Trees all over the place are dying. And so the western United States is going to start looking really, really different when a lot of these conifer forests are no longer there. And this is a consequence of warming temperatures in the western United States. One of the other consequences is less water in the Colorado Basin. Southern California and Arizona get a lot of their water from the Colorado Basin. And at the moment, they're oversubscribed. In other words, the 1923 Basin Compact that the Colorado Basin states came up with, there's not enough water to satisfy the compact. And there's an expectation over the next few decades that because of the decrease in water in the Colorado Basin, we're going to have severe water shortages in places like Arizona, Phoenix, and Tucson, and LA, which get a large part of the water from the Colorado Basin. This is a coral. Well, hey, wait, I thought corals were kind of like pretty colors. Corals are colonial organisms. Each of these little bumps here is where a little coral polyp, an animal, lives. And they sit there and they filter feed. And they together build these big structures out of calcium carbonate. Now, they also live symbiotically in partnership with photosynthetic algae that are actually in the little coral polyp. And so the coral polyp grabs food by filtering, gives it to the algae uses sunlight and makes food for both of them. This is why corals can be very, very biologically productive in really clear ocean water. Clear ocean water means not a lot of food. And so, but corals being in water in the tropics, which is one of the most stable biological environments on Earth, are not very tolerant of changes in water temperature. So when water temperature rises, they get stressed. And when they get stressed, they say to these little symbiotic algae, they say, hey, yeah, I remember all the good things you did for me, but sorry, boom, and they kick them out. This is called bleaching. And when they do that, they turn white because the algae would give the corals off in their color. Corals can stand being bleached occasionally, but if they get repeatedly bleached, they die. And so about 70% of the coral in the Florida Keys is now dead. I mean, the change that I've seen in just being in Florida for this, embarrassing to say I've been here 38 years. The first time I dove in the Keys was 40-something years ago. And the change in the reefs down there is just amazing. There's, all of the branching corals are pretty much gone. The massive corals, you see these big brain corals, and they're either dead or half dead. It just looks, there are hardly any fish on the reef. It just looks so different. One of our graduate students who now is doing work on salmon in Alaska, before he came to us, his job was he started each year up on near Palm Beach and Jupiter and looked at reefs, so all the way out to the dried Tortugas, and basically did a reef assessment. That's his job. He did that for 10 years. And I said, why would you leave that job? I mean, it's a fantastic job. You get paid for diving on reefs all year long. And he said it was getting too depressing because he was just basically cataloging this huge decline. So reefs are in trouble both because of rising water temperatures, also from pollution. And one of the other problems is that as the amount of carbon dioxide in the atmosphere increases, it dissolves in seawater, and seawater goes towards a more acidic. It still basic less than 7, a number greater than 7 pH, but as it gets more acidic, it's harder and harder for these little guys to precipitate that calcium carbonate from seawater. This little guy is pretty, not particularly important biologically, just has the unique distinction of being the first vertebrate that we know of that went extinct because of climate change. This little guy was endemic to a small area near Monteverde in Costa Rica. It's a cloud forest. It's the Central Cordillera of Costa Rica, and the trade winds bring this moisture up, forms clouds, and the rainforest, cloud forest actually intercepts the clouds. And so the clouds would condense on the trees, and up to 1 meter of water would basically be cloud moisture. And so in the wet season, these ponds would form in the cloud forest, and these little guys would breed in these wet weather ponds. Well, the cloud base has gone up at Monteverde, and the result is the cloud base is often above the trees now. And so there's been a substantial decrease in the available moisture in the cloud forest. The wet weather ponds no longer form, and this guy was last called the golden toad. This guy was last seen in the 1980s, and it's the first vertebrate that has been documented to have gone extinct. So again, not a particularly important organism, but one that was a victim of climate change, this rise in the cloud base as the temperature has warmed. All right, so why is the climate changing? All right, greenhouse effect. This is a bad name. It probably should be called the blanket effect. Let's say it's a cool night, and you climb into bed with just your skivvies on, and you're laying there and you say, hey, I'm cold. So you pull a sheet up over you, right? That makes you a little bit warmer. Why does it make you warmer? Because your body is giving off heat. Right? And when you pull a sheet over you, it's a little bit more difficult for the heat to go through that cloth because it insulates, it absorbs some of that heat. And so what has to happen in order for your skin temperature to stabilize, you have to increase the temperature gradient through that sheet. And so that means your skin temperature rises a little bit. And then you imbalance between the heat your body's producing in a cool room. But maybe your skin temperature's not high enough yet, you're still cold, so you pull a blanket on. And what that does is the same thing. It insulates, it absorbs some of the heat coming off of your body and radiates it back towards you. And so in order for you to be in heat balance between the room and you, your skin temperature increases. And so you feel warmer. And so this is called the blanket effect. And the atmosphere is a blanket effect. It absorbs some of this thermal radiation that's coming off. By the way, radiation doesn't mean nuclear radiation, it just means light. That's what we call it, radiation. So thermal energy coming up from the Earth is absorbed by gases in the atmosphere, and some of that energy is then radiated back down, and some goes out. Because some of it's going down, in order to balance the temperature, the energy going out and the energy coming in, we have to raise the temperature of the surface of the Earth a little more, just like your skin temperature gets raised when you pull a blanket on. So it's called a greenhouse effect, but really it's probably more aptly called a blanket effect. So the atmosphere basically absorbs some of this energy that's being sent out to space and raises the surface temperature of the Earth. At some point, we come back into balance and the temperature stops increasing. The good news is that the amount of energy that anything, you, this object, that bottle of sanitizer radiates, depends on the fourth power of its temperature. So we don't have to change the temperature of the Earth very much in order to get everything back in balance. That's a good thing. But even small temperature rises are a problem. If we didn't have an atmosphere, the temperature of the Earth would be average temperature would be about 0 degrees Fahrenheit. It's actually about 55 degrees Fahrenheit. So we have a nice habitable Earth because of the atmosphere. The greenhouse effect is a good thing. Now, the principal gases that absorb this energy are carbon dioxide, methane, and nitrous oxide, and water vapor. Why is it water vapor up there? Because we don't control water vapor. Water vapor, the amount of water vapor in the atmosphere depends on temperature. And it comes into equilibrium really quickly. If you crank up a climate model without any water vapor in the atmosphere, within 2 or 3 days of simulated time, the water vapor in the atmosphere is back in normal balance. So that's a very rapid adjustment. We don't control the amount of water vapor, so it's not considered to be a so-called anthropogenic greenhouse gas. But we do influence the amount of carbon dioxide, methane, and nitrous oxide. Methane and nitrous oxide, the principal sources are agriculture. Methane is also, this is natural gas. And so when we develop natural gas, some of it is released, and that contributes methane. Carbon dioxide principally comes from the burning of fossil fuels, and I'll show you how we know that in just a second. So what you can see is this is 10,000 years, this is 0 years, and in all of these there was a decline until about 7,000 years ago on carbon dioxide, and then it started increasing. Bill Rudiman at the University of Virginia has a theory that this corresponds to the start of agriculture. And so his theory is that the start of agriculture and deforestation actually stopped this downward slide of carbon dioxide, which is what happens after you're coming out of a interglacial like we had 10 or 12,000 years ago. But this downward slide was halted by the human effects. This, of course, is a really rapid rise in carbon dioxide. What happened in 1763 that would strongly affect the amount of carbon dioxide going into the atmosphere of fossil fuels? Anyone know what happened in 1760? Yeah.
Industrial Revolution?
It is, right. Do you know what the single event that is, if you had to pin anything on the Industrial Revolution on anything, what it was? How do you measure the output of a light bulb? What do we call it? Watts. Who's that named after? James Watt. James Watt did not invent the steam engine. He improved it. He improved it a lot. And he and his partner, Bolton, in 1763 patented the Watt and Bolton steam engine, which was a vastly improved steam engine. The first thing they used the steam engine for was pumping water out of coal mines in Wales and Cornwall. And so all of a sudden, they could mine deeper, they could mine cheaper, and there was, Great Britain had this sudden abundance of coal, cheap coal, and they had a way to use it, a steam engine. Bingo, Industrial Revolution and the British Empire, based on coal. Right? The 20th century was the United States' big empire. What was that driven by? Not so much coal, we use a lot of coal. We became, up until 1970, we were one of the principal producers of crude oil in the world. Right? And so basically there's this correspondence between energy use and GDP. Basically the Industrial Revolution was because of the fact that we had, one, abundant, cheap fossil fuels available and a way to use them. And so we suddenly started using lots of fossil fuels. At the same time, coal mining also releases methane, but it's also agricultural. This is ruminants, like cows that have multi-part stomachs, they burp methane, so do termites. And also the decay of manure produces methane. Nitrous oxide is probably about a third to half of the people on the globe today are alive because we actually have an artificial part of the nitrogen cycle, and we put artificially produced nitrogen on their crops, and a lot of that then ends up going back by what are called denitrifying bacteria, go back to the atmosphere as nitrous oxide. All right, so global climate drivers. These are the things that influence climate, and this is by year. And one of the obvious ones is the sun, right? If the sun gets less energy, it's going to get cold. If the sun has more energy, it's going to get hot. So that's a really important one. And so that's this one right there. It turns out that there have been changes in solar energy, but they contribute relatively little to the change in climate. The big driver has been the change in greenhouse gases. Now, one of the other ones is volcanic eruptions. Every time you throw a lot of ash and sulfur dioxide into the atmosphere, it reflects sunlight and it cools the atmosphere. But that only lasts for a few years. The other thing is when we burn coal, those sulfur dioxides go into the atmosphere and they turn into sulfuric acid and they reflect sunlight. And so these are called aerosols, another bad word that climate scientists use. It's not a spray can, it's just particles in the atmosphere. We call it an aerosol. So aerosols, particularly sulfur dioxide, basically is cooling the earth. If it wasn't for the fact that we're burning coal, and the coal sort of offsets itself a little bit because it puts sulfur dioxide in the atmosphere, which reflects sunlight. But the main contributor has been greenhouse gases. The solar energy, actually, this is the solar sunspot cycle, that little wavy part, but average solar energy has actually decreased since about 1950, because we measure that one directly, that's easy to measure. Now, this is a graph which can be I suppose looks good, but you got to be really careful. This is an example of correlation. Right? So the blue and red are temperature, average global temperature, and this is an absolute temperature Fahrenheit. And what you can see is from the 1880s up through the 20th century, there's a general increase in average global temperature. And during the same time, there's been an increase in CO2 concentration. This is basically the method that the BEST group used. They basically did a multi-parameter regression and statistical regression. They just threw all of the possible climate change drivers into an equation and crunched it and said which of these are significant. And there were only two that were significant: volcanic eruptions and carbon dioxide. And so they said, yep, this graph shows that carbon dioxide is it. But you always have to be careful. This is correlation. You have to be careful. Correlation is not causation. All right? The fact that two things are correlated. For example, let's say I wanted to figure out why people become addicted to heroin. Go, well, maybe it's something in their background. Well, let's run the numbers. My God, I got it. Almost every single heroin addict drank milk as a child. Meaningless, right? Meaningless. But they're highly correlated. So you got to be careful with correlating, but what you need to look for is a reason why they should be correlated. This is a greenhouse gas, and from simple physics we've known for 200 years, we know that if carbon dioxide, and also from the geologic record, we know that if carbon dioxide goes up, the temperature goes up. And so in this case, the correlation is a valid one. This is a graph. This is solar insolation. This is the amount of solar energy coming in at the top of the atmosphere, which we measure from satellites, starting back here. But we can also estimate it from sunspots because those are related. And this is global temperature. And so you can see that starting in the 1960s, global temperature started to rise very rapidly. During that same period of time, average solar energy striking the Earth remained about the same or went down a little bit. So you can't say that this rise in temperature was due to a change in solar energy. On the other hand, in the early part of the 20th century, there was a rise in global temperatures, and there was a corresponding rise in the sun. But the problem is that they get out of sync sometimes. Here's solar energy going down, temperature kept on going up. Here's solar energy reaching a peak, and the actual temperature went down. But this in particular shows that this recent rise in temperature can't be due to change in the sun because they're going in the opposite directions. All right, there's some fingerprints that tell us where this warming or change is coming from. We have satellites going around the Earth. They're measuring the thermal energy coming up, and they're measuring it by wavelength. And different specific gases absorb specific wavelengths. So we can look at the brightness, relative what's called brightness, and basically this is methane absorbing thermal radiation. And so we can actually, these are some others, these are chlorinated hydrocarbons, CFCs, like this is halon, this is the stuff that we used to use in fire extinguishers and aerosol cans. And so we can actually tell the relative contribution of each of those atmospheric gases to the warming by looking at this. And this fingerprint tells us that carbon dioxide and methane, which are measured to be increasing, the amount of thermal energy being absorbed in the atmosphere is also increasing. Those are from direct satellite measurements. The other thing is if the atmosphere, lower atmosphere, is absorbing this thermal radiation, there ought to be more downgoing thermal radiation. And there is. That's what the red means. This means an increase. There aren't any data here because the data periods didn't overlap when we did this analysis. So that doesn't mean it isn't happening. It's just been excluded. But you can see all of this red means more downgrowing thermal radiation. It's another fingerprint. The other thing is that, especially in this last big warm-up, it's getting warmer at night. It's getting warmer in the winter. And it's getting warmer in the lower part of the atmosphere, and the stratosphere is cooling. Those three things tell you, one, that the atmosphere is warming from the bottom up, and the second, it is warming because less heat energy is escaping in the winter or at night. If it was due to an increase in the sun, we would expect the atmosphere to warm from the top down, and we would expect the higher temperatures to be during the day, and we would expect them to be during the summer. And we see exactly the opposite. So what's happening is the atmosphere is warming at night in the winter and from the bottom up, which suggests that it's because of this increased trapping of heat as a result of greenhouse gases. This is the troposphere, which is where we live, the lower part of the atmosphere, and it is warming. Less heat is getting out to the upper atmosphere, which is the stratosphere, and it is cooling. Another fingerprint for warming from the bottom up. Satellites show us exactly the same thing. The further you go up in the atmosphere, the less the warming till you get to the tropopause, which is the difference between troposphere and stratosphere. As soon as you get into the stratosphere is cooling. What this is this is from the North Atlantic. This is depth here. And basically the red shows you the relative shift in temperature over the period of record, which is the latter part of the 20th century. And so the oceans have warmed. And so if we run our ocean circulation models with natural drivers of climate, we get these greens here. And this is our uncertainty in our answer. And so basically, using natural drivers of climate, we can't duplicate the data. If we include the increase in greenhouse gases and run our models, we get this green area here, and that better matches the actual observed data. Here's another example. This black line is the observed temperature change during the 20th century up to 1995. And this represents a series of climate models, their prediction, starting running the models in 1900 and letting them run forward in time. And they closely duplicate the pattern that we actually observe. And then you go inside the model and say, okay, well, how did I have to adjust these dials to make my model actually mimic the real climate? And what you can see is in the early part of the 20th century, solar, which is red, had about an equal contribution as greenhouse gases. But starting in the late 20th century, the greenhouse gas increase overpowers everything else. Here's sulfate. That's the cooling one that I told you about. Right now, we've had about a 0.7 to 0.8 degrees Celsius temperature change globally. But there's about a minus 0.3 due to sulfate. Ironically, if we clean up the atmosphere, like China's now trying to do because they have such bad pollution, we will actually increase heating because we're going to get rid of some of those sulfates in the atmosphere. All right, so how do we know we're responsible? All right, this is years before present, 420,000 years out to the side. This is atmospheric carbon dioxide. You go, oh, wait a minute. How can you measure carbon dioxide 400,000 years ago? Right? That's a good question. If you're at the Greenland or the South Pole, these data come from Antarctica. If you're at the South Pole when it snows, very little of that snow melts, and so it starts to pile up. And so the weight of the snow, those little snow crystals, they start to meld together, and they form ice. Right? And so eventually you form ice, and there's about 10,000 feet of ice in East Antarctica. As those snow grains are coalescing, they trap little bubbles of the atmosphere. And those bubbles are still there. And those are basically little samples of the atmosphere at the time that those holes closed up. It takes about 50 to 70 years for those holes to close up, to go from snow to ice in Antarctica. So that means if I look at 50,000-year-old ice and I extract the gases from it, that's a sample of the atmosphere 50,000 years ago. In addition, oxygen comes, as I'll tell you in a second, oxygen comes in two different isotopes. There's oxygen-16, which has 6 neutrons and 6 protons, and oxygen-18, which has 2 extra neutrons, so it's heavier. When water vapor condenses to water, the heavier oxygen is favored because thermodynamically, because it's heavier. And the ratio, that's called fractionation, and the ratio between the oxygen-16 and 18 in that fractionation depends on temperature. So the ratio of these two isotopes of oxygen is basically a thermometer. So ice is H2O. So we can look at the oxygen isotope ratios of the ice, and it tells us the relative temperature at which that ice formed. Right? And so we can tell the relative temperature change at any place in the ice from the oxygen isotope ratios. By calibrating that to modern temperature data, we can actually turn it into an absolute thermometer. So we can tell, and then we can radiometrically date the age of the ice. And so we can tell the age of the ice, the carbon dioxide content, and the temperature. All right, so this is from the Vostok station, and it's the coldest place probably on Earth. Average temperature, annual temperature, about minus 55 degrees Celsius. And this is the record of atmospheric carbon dioxide versus time. Last ice age, low carbon dioxide, we came out of it. Okay, this was the last interglacial about 125,000 years ago. Ice age, interglacial, ice age, interglacial, ice age, and interglacial. The maximum, if we go back a little bit further, we get a maximum value of about 300 parts per million carbon dioxide in the ice. Last spring, late in March or April, we hit 400 parts per million. So we are now, there's now another ice core called the Epoca ice core from the European group that goes back 800,000 years. And that, again, this is the maximum, just a little bit below 300. The Epoca doesn't have anyone any higher than that. And so basically, the highest the carbon dioxide has been in the atmosphere in the last 800,000 years, about 300 parts per million. And we're just about 400 right now. Right? And so we're right here. This is carbon dioxide concentration, and these are largely Vostok data. And this is the relative temperature change based on that oxygen isotope data. And remember that 5 doesn't mean 5 degrees above 0, it means 5 degrees above minus 55 degrees Celsius. Pretty cold in Vostok. But this is basically higher carbon dioxide concentrations. These are the interglacials. This is lower carbon dioxide concentrations and lower temperatures. These are the glacials. And it's been cold for a lot more than it's been, longer than it's been warm in the last 420,000 years. If I draw a line, these basically incorporate all the data from about 1700 to 400,000 years ago. If I draw a line through that, that's the relationship between carbon dioxide and temperature at Vostok. And so here are modern data, 2011, 2012, and 2013. If I take this 2013 carbon dioxide amount and go back up to that line, it predicts about a 12 degrees Celsius rise in temperature at Vostok. And so basically, modern temperatures at the Vostok station in Antarctica are way out of equilibrium with the relationship between carbon dioxide and temperature for the last 420,000 years. All right. Carbon isotopes. Carbon-12, 6 neutrons, 6 protons. Carbon-13, 1 extra neutron. Both of these are stable. Carbon-14 is radioactive. It decays. Okay? Has 2 extra neutrons. It has a half-life about 5,700 years, which means every 5,700 years, half of it is left. So if you take something that contains carbon-14 in equilibrium in the atmosphere and you shut it away, after 50,000 years, there's basically no carbon-14 left. All right, so when plants pull carbon dioxide out of the atmosphere, they prefer carbon-12. And so there's a fractionation. So photosynthetic carbon is enriched in carbon-12 and depleted in carbon-13. And fossil fuel carbon is depleted in carbon-14 because it's older than 50,000 years. So carbon-14 is created in the upper atmosphere from charged particles from the sun. So there's an atmospheric concentration. And as soon as you lock something away, that carbon-14 starts to decay. That's how we date things with carbon-14. And photosynthesis prefers carbon-12 over 13. So if there's a decrease in the amount of carbon-13, it means that indicates photosynthetic carbon. So no carbon-14 and depleted C13 is an isotopic fingerprint for fossil fuels. This is relative carbon-14 concentration, and you can see, boom, starts to drop off right around the early 1800s. That's fossil fuel carbon being added to the atmosphere. It's not volcanic. Okay, you say, okay, well, maybe this is, what's going on here? What's happening? Well, there's another fingerprint. That dark line there is carbon dioxide, and it's plotted backwards, so this is high CO2 down here. And these others are basically the ratio of carbon-13 to carbon-12, and that ratio starts to change very dramatically right in the 1700s. So basically, we have both fingerprints for fossil fuel carbon. We have depleted carbon-13, that means it's photosynthetic carbon, and it's old carbon, because there's no carbon-14. And so those two fingerprints tell us that the new carbon in the atmosphere, from 300 to 400 parts per million, is principally fossil fuel carbon. The last thing is if we burn fossil fuels, we use oxygen. As carbon dioxide goes up, oxygen goes down. Don't worry. There's a lot of oxygen in the atmosphere. The amount we're burning is relatively small. We don't have to worry about breathing. But there's a very distinctive signature of increasing carbon dioxide, decreasing oxygen. That would not happen, for example, if it's coming from volcanoes. With volcanoes, it's already coming out as CO2. It doesn't affect the amount of oxygen in the atmosphere. So this is a fingerprint for non-volcanic fossil fuel carbon. All right, so carbon dioxide absorbs thermal energy emitted from the Earth's surface. We know that from basic physics and direct measurement from satellites. CO2 levels are increasing. We've measured it accurately over time scales of decades to millennia, and additional carbon dioxide, the new carbon dioxide, has fingerprints that shows that it's fossil fuel carbon dioxide. The temperature of the lower atmosphere is increasing. We've measured it directly, and that's what we expect from physics as we increase the concentration of greenhouse gases. So the global average temperature is increasing, and the principal cause of the rapid rise in temperatures since the mid-20th century is the increase in greenhouse gases, notably carbon dioxide from burning of fossil fuels with a 95% certainty in the latest Intergovernmental Panel on Climate Change 2013, and also the Koch-funded BEST group has decided that both of those things are true. So, thanks.